Greetings, this is Professor Roman. We'll continue our discussion of linear algebra. I mentioned some time ago that one of the main themes in mathematics is to find ways to construct new objects from existing objects. We've seen a number of examples of that. As I recall, when I first discussed this issue, I mentioned just set theory, the operations of union, intersection, symmetric difference, relative complement, Cartesian product, power set. Those are all ways of constructing new sets from existing sets. In linear algebra, we've seen that if you take two vector spaces over the same field, you can form their Cartesian product and use element-wise operations to get the external direct sum, which is another vector space. If you have two vector spaces over the same field, then the family of linear transformations from one space to the other also forms a vector space. So those are two examples of creating new vector spaces from existing vector spaces. Another way to do that is to form quotient spaces, which is the subject of this lecture. And I want to start with some motivation. Here's a reasonable question. Suppose you have a vector space V and you have a partition of V. So this is a picture of B, C, D, E. Those are blocks of the partition. There may be others, of course. How can we use the vector space structure on V to make the blocks of the partition into vectors for another vector space? Obviously, we want there to be a connection between the vector space operations on the blocks and the original vector space structure on V. Well, of course, in order to make this partition, let's call it P, into a vector space, we have to define the two vector space operations, addition and scalar multiplication, on the blocks of the partition. There seems, as far as addition is concerned, seems to be only one way to proceed that ties the operation into the original operation on V. If we have two blocks B and C and we want to define their sum, we take a vector U in the block B and a vector V in the block C. We can take the sum, U plus V. That vector has to lie somewhere in the vector space, of course, and therefore in exactly one of these blocks. Let's say it lies in block D. D could be B, it could be C, or it could be another block. Then we set B plus C equal to D. There is, however, a potentially fatal problem with this, shall we call it, definition of block addition. And that is, it may not be well defined. It does depend on the choice of vector from the two blocks. So if U prime is also in B and V prime is also in C, there's no guarantee that the sum U plus V and the sum U prime plus V prime have to lie in the same block of the partition. if u prime plus v prime is in block d prime, and that's different from d, we have a problem. Because now we have two different ways to compute the sum b plus c. In one case it comes out d, in the other case it comes out d prime, and of course that's nonsense. So if we want this block addition to make sense, to be well defined, we must have the following property, that if u and u prime are in the same block, and v and v prime are in the same block, then u plus v and u prime plus v prime must be in the same block. Then this operation of block addition will be well defined. It'll make sense. It'll be a legitimate binary operation on the blocks of the partition. We can be a little bit more formal by passing to the same block equivalence relation, and that, as you may recall, is u is equivalent to v if u and v are in the same block of the partition. So then this condition that we need becomes u equivalent to u prime, v equivalent to v prime, implies u plus v equivalent to u prime plus v prime. We have a similar problem in defining scalar multiplication. The what you might call obvious approach is to define a scalar times a block, Rb, by taking any vector in B, call it V, in B, computing this scalar multiple, Rv, that lies in some block, C of the partition P, and then set Rb equal to C. But, as with addition, this definition of block scalar multiplication depends on the choice of vector. So, to eliminate this problem, we must have u equivalent to u prime implies ru equivalent to ru prime, and I should say for all the scalars. Okay. We can combine the two conditions, the one that makes addition well defined and the one that makes scalar multiplication well defined, in one condition. U equivalent to u prime and v equivalent to v prime implies ru plus sv equivalent to ru prime plus sv prime. And again, for all r and s in scalars r and s. So, if we expect these two operations, block addition and block scalar multiplication, to be well defined, we require this property. And now we need to determine which partitions of a vector space, if any, satisfy this condition. The key to determining that is to examine carefully the block of the partition, which I'm going to call B naught, that contains the 0 vector. There's only one block in any partition of V that contains the 0 vector. That's a special block. The other blocks have no particular distinguishing features. This is the block that has the 0 vector and sort of stands out among all the blocks of the partition, so we need to take a careful look at it. if we take u prime equal to v prime equal to 0 in this condition, let's call this the well-definedness condition, then we get u equivalent to 0 and v equivalent to 0 implies Ru plus SV equivalent to 0. Or in terms of the block B naught, if u and v are in B naught, then so is Ru plus SV. Well, for all Rs in it. At least you can say I'm consistent. I miss this every time. This, however, is precisely the statement that B naught is a subspace of V. No other block could be a subspace because no other block contains a zero vector, for example. But there's no reason to believe that just because we partition a vector space in any way we want, chop up the vector space into blocks, that the block containing 0 is going to have to be a subspace. So that is a necessary condition. It follows from the well-definedness condition. But we're not done yet. That's not enough. Just because the block containing 0 happens to be a subspace of V does not imply that the operations are well defined. It's a necessary condition but not sufficient. In fact, our well-definedness condition gives us a lot more information about the partition than just the fact that B naught is a subspace. It, in fact, describes every block of the partition. Specifically, let B be a block of the partition and let U be a vector in B. Then for any vector V in B, our well-definedness condition tells us that V equivalent to U, they're in the same block. U, of course, is equivalent to U, and therefore V minus U is equivalent to U minus U, which is 0. These are linear combinations of VU and UU. And that implies that V minus U is in B naught, equivalent to 0. And that implies that V belongs to this set, U plus B naught, where U plus B naught is defined this way. This is something we discussed when we first talked about vector spaces, that you can use the vector space operations not only on individual vectors but on subsets. So this is a little bit of an abuse of notation. It should look, strictly speaking, like that. The set containing only the vector U and the set B naught, we can add these. It's simply the set of all sums of a vector in this set and a vector in this set. So it's all the U plus X's where X ranges over B naught. So what this tells us, this computation, is that if V belongs to B, then it also belongs to this set, U plus B naught, which means the block B is contained in U plus B naught. On the other hand, if we take a vector from B naught and use our well-definedness condition again, u equivalent to u, v equivalent to 0. That's where we got v from. That implies that u plus v is equivalent to u plus 0, or u. And that implies that u plus v is in the block B, because that's where did it go? There's where u came from, not v, u came from B. And that implies that u plus b naught is contained in the block B. So these two blocks are equal. So the well-definedness condition implies two things: that B naught is a subspace of V, and that the blocks of the partition must all have this form, a vector plus B naught, that special block. This set, described here, is called a coset of B naught. And so the blocks of the partition P are the cosets of B naught. So it all comes down to B naught. The subspace, the block that contains 0 is a subspace. Once that is known, the whole partition is determined, if we want the well-definedness condition to hold. And there's no reason why B naught can't be any subspace. We're free, the partition was arbitrary, so to guarantee that the two operations we've defined are well defined, we start with a subspace. And that subspace, which is denoted here by B naught, determines the partition under which these two operations are well defined. So that's the story. And now that we understand where this is coming from, what we're going to see is that the collection of cosets, the partition of V into cosets, is another vector space. Those two operations, once they're well defined, that's the hard part. The rest is not so bad. You can show that block addition and block scalar multiplication make the partition of V into cosets into a vector space called a quotient space. So now it's time to start over and do this a little more formally, as you would find in most books, I think. But at least you understand the motivation behind the upcoming discussion. If S is a subspace of a vector space V, then we can define a binary relation on V by U equivalent to V if and only if U minus V is in the subspace. Another way of saying this is that U is in the coset V plus S, or that V is in the coset U plus S. We'll come back to that. We're starting over, so we don't know what a coset is at this point. This is easily seen to be an equivalence relation. When U and V are equivalent, we say that U and V are congruent modulo the subspace S, or congruent mod S. Mod is a short way of saying modulo. And we might write this: U congruent to V mod S. That just simply means that U minus V belongs to S. This is not the same block equivalence relation that we discussed earlier. It's different. When the subspace S is clear, I may just write U congruent to V. So, what do the equivalence classes look like for this equivalence relation? Well, if we take a vector, little v and v, denote its equivalence class as we have in the past by v in square brackets, then that is by definition the set of all vectors u and v that are congruent to v, or in other words, for which u minus v is in S, or in other words, for which u equals v plus little s, for some little s in the subspace. In other words, it's the coset v plus s. So, S determines the entire partition. It is the partition of cosets of S. So again, here's the definition of coset, v plus capital S. This is called a coset of S, not of V, but of S, in V. And little v is called a coset representative for the coset v plus S. So, just in summary, we defined an equivalence relation this way. It might seem a bit odd at first. Why would we do that? But you have to stay tuned, although the motivation we just gave will explains why this is the correct equivalence relation. And we immediately said, well, gee, this is an equivalence relation. I wonder what the partition looks like into equivalence classes, and we discover it's the cosets of S. And we have yet to prove that the vector space operations, the block addition and scalar multiplication, do form a vector space. We'll get to that. It is a bit sometimes tricky to work with cosets, especially when you first encounter them. And the main reason is that every member of a coset, every v plus little s, is a coset representative for this coset, because little v plus little s plus capital S, this coset, is the same as this. I've just reassociated here. And little s belonging to capital S implies that little s plus capital S is just capital S. What you do when you add a vector in capital S to capital S, to the subspace S, is you just shove everything, or scramble it all internally. So you still get the subspace S. This is because S is a subspace, of course. So there's nothing at all special about this particular V. It could have been any vector in the coset. And so what you have is a lot of redundancy in the expression of a coset. You can express it in a lot of different ways because you can pick any vector in the coset and use it as a coset representative. And as we'll see a bit later, this can cause some issues that need to be addressed. It's nothing that's unsurmountable. It just has to be paid attention to. One of the most important properties of cosets is this following simple result concerning equality of cosets. Again, generated by or required by this issue of non-uniqueness of coset representatives. When are two cosets equal? It's not only when u equals phi. Certainly if u equals phi, they're equal. But these two cosets are equal if and only if u belongs to the coset represented by v, or equivalently, v belongs to the coset represented by u, or finally equivalent to u congruent to v mod s. The proof is short, and I'm going to skip it because I think it would be good practice for you. It may take a little effort to get used to handling cosets, and we're going to discuss that in more detail. But the only way you're going to do it is by practice. So I suggest you try to prove this theorem yourself. So the set of all cosets of a subspace S of V is denoted this way. V slash S. This is read V mod S. It's this set of cosets of S in V. It is called the quotient space of V mod or modulo S. V mod S, the quotient space. It's also called a factor space. And one says that S is factored out of V to obtain V mod S. Now, of course, referring to this as a space would be ill-advised unless, in fact, this was a vector space. So, we need the two vector space operations, and they look like this. Coset plus coset equals coset. What we are doing is exactly what we did in the motivational discussion earlier. We're taking a vector v in this block of the partition, or in other words in this coset, taking a vector u. We're taking a vector v from this coset. We're adding the two vectors that we picked out of each block, and then we're defining the sum of these two blocks to be the block containing u plus v. I guess I should have said, although it's quite obvious, v plus s, this coset, does contain v, because s contains the zero vector. Similarly, we have scalar multiplication this way. To multiply a coset by a scalar, multiply its representative by that scalar and find this coset. Now you can see quite clearly that these two operations depend, at least apparently depend, on the choice of coset representative. But in fact, they do not. For if u1 plus s equals u2 plus s, so we've got two different coset representatives for the same coset, and the same for v1 plus s and v2 plus s, then according to our operations here, ru1 plus sv1 plus s is equal to ru2 plus sv2 plus s. This is what we need to show. This is the condition that these operations are well defined. But this follows quite easily from the fact that S is a subspace. So we have our two expressions for these cosets. By definition, by the earlier theorem, this is equivalent to u1 minus u2 is in S. This is equivalent to v1 minus v2 is in S. Because S is a subspace, then this linear combination belongs to S. We unscramble it, showing that the two cosets are equal. So, we have now seen that the quotient space has two well-defined operations, addition and scalar multiplication. The rest is showing that those operations are in fact vector space operations. That coset addition is associative, and that's going to follow from the fact that the addition in the original vector space V is associative. That there's a zero vector in V mod S, and so on. You have to check the definition of a vector space, and I'm going to let you do that. But I want to make certain that you understand what the zero vector is in V mod S. This is often confusing to people who first are studying quotient spaces. It's the zero coset, 0 plus S. This is the zero vector in V mod S. But of course 0 plus S is S. So S itself, the subspace S, is in fact the zero vector in the quotient space. Just as a simple example, suppose that S is the two-dimensional subspace generated by these two vectors in R3. Then the quotient space R3 mod S is, again, simply the set of all cosets of S in R3. But we have the issue of redundancy in this description. Several V plus S's are the same coset. You can take any vector from the coset, stick it here for V, you'll get the same coset. For example, 111 plus S is the same coset as 334 plus S. It certainly doesn't look like it when you just stare at this. But if you subtract these two vectors, you will get a member of S. And so these are in fact the same coset. This is where the trickiness comes in working with cosets. It's not the only situation where we have this sort of several different ways to write the same object. 1/2, 2/4, 4/8. These are all the same rational number. And that's pretty obvious, I guess you would say, because you're so used to working with these. These are the same coset, even though on first inspection you can't tell they're the same. You have to take the difference and you have to set up a system of linear equations to make sure that difference does belong to the subspace. So it's not at all as obvious. Equality of cosets is not nearly as obvious as equality of fractions, at least some fractions. As we saw in this example, the general definition of quotient space suffers from considerable redundancy. Now, if S is the trivial subspace, there is no redundancy, because then there's one vector in each coset. This reduces to singleton subsets. But otherwise, as long as a coset has more than one vector in it, it has more than one coset representative, and we have our problem of redundancy in the description of V mod S. How can we get a redundant free description of the quotient space? In other words, we want one and only one coset representative from each coset. No problem. Just pick one vector from each coset, say T1, T2, T3, and so on. Put those vectors in a set, capital T. Then this family, T mod S, of cosets of S and T, so we're only using those single vectors from each coset as coset representatives. We're not allowed to use any other coset representatives. Now we have a description of V mod S that has no redundancy. Every coset of the form T plus S, as T ranges over capital T, is different. And of course we have a full representation of the cosets because we've chosen one vector from each coset. So T mod S equals V mod S. This set T is in fact a system of distinct representatives of the cosets. That's a generic term, general term. In this context of linear algebra, vector spaces, quotient spaces, T is called a transversal for the quotient space. Just one vector from each coset, called a transversal. Before I give you a formal definition of transversal, though, there is one point that needs to be addressed. When we write T mod S and read this T mod S, we've extended the notation and the terminology. Hitherto, we referred to V mod S and called it a quotient space. But V was a vector space and S was a subspace of V. In T mod S, T does not have to be a subspace. Remember, it's a transversal. It's one vector from each coset. It doesn't even have to include the zero vector unless S is a trivial space. So T does not need to be a subspace. We'll look at that more closely in a minute. Even if it is a subspace, it's unlikely to contain S. So this expression, T mod S, is a different beast from V mod S. This is not a vector space. It's not a quotient space. This is a quotient space because V is a vector space and S is a subspace. This is, I suppose you could call it a quotient set. Might be a little dangerous because some might misinterpret that. So we'll just refer to it as T mod S. And since this is such a convenient notation, here's a formal definition of this. V is a vector space, S is a subspace of V, X is any non-empty subset, then X mod S is simply the set of all cosets where the representatives come from the set X. This is also read, I guess I should say, X mod S. Okay. Now I can give a formal definition of transversal. It's the same as what we've just discussed. S is a subspace of a vector space V. A transversal T for the quotient space V mod S is a set consisting of exactly one coset representative from each coset. Or, in other words, a system of distinct representatives for the quotient space. So, as we've said before, T mod S is the same as V mod S. Well, given a quotient space, V mod S, we would like to know which subspaces of V, say column T, are transversals. According to the definition of transversal, for each vector little v in capital V, there is a unique little t in the transversal for which V is in this coset represented by T. Or in other words, for which V equals S plus little t, and therefore that makes little s unique because obviously it's V minus t. In other words, every vector is a sum of something from S and something from T. S is a subspace. T is now we are assuming to be a subspace that's a transversal. Okay? So which subspaces T of V are transversals? So this says that every vector little v in V has a unique representation as a sum, little s plus little t, where little s is in the subspace S and little t is in the transversal subspace. In other words, this is a direct sum. And so T is a direct complement of S. So a subspace that is a transversal, I'll call it a subspace transversal subspace. I guess that sounds better. Transversal subspace must be a direct complement of S. A transversal subspace, transversal for V mod S, that is also a subspace, must be a direct complement of S. The converse is also true. Every direct complement T of S is a transversal for V mod S. In other words, it's a transversal subspace of V. Transversal for V mod S, subspace of V. Let's look at that formally. Let S be a subspace of a vector space V, then a subspace T of V is a transversal for V mod S if and only if T is a direct complement of S, this way. And we've already seen that a subspace that is a transversal is a direct complement. We need to check the converse. So we assume that V is a direct sum of S and T. Then every vector, little v, is a unique sum S plus T. S belongs to capital S, T belongs to capital T. And so V plus S, this coset, is S plus T plus S, which is T plus S. Again, the little s gets absorbed into the subspace capital S. So the set capital T does contain a coset representative for every coset. This is an arbitrary coset of V mod S. It can be written this way, where little t comes from the complement, capital T. So T mod S, I guess I should have written that. T mod S is the same as V mod S. But also, little t is unique because if we have two cosets with representatives t and t prime from the complement capital T, and those are the same coset, then t minus t prime belongs to S because of this condition, but it also belongs to T because T is a subspace of V. So it belongs to the intersection, but because this sum is direct, that intersection is trivial. These are essentially disjoint, and so T equals T prime. So the cosets little t plus S, as little t ranges over the direct complement, T of S, are distinct, and we have this equation. In other words, T is a transversal for the quotient. So again, we have a subspace S of V, the transversal subspaces, the transversals that are, for V mod S, that are subspaces are precisely the direct complements of S in V. And as you know, these are far from unique in general. So there are many transversal subspaces in general. Actually, the connection between quotient spaces and subspace transversals, or transversal subspaces, I don't know. I guess it doesn't matter which way I do it. Let's say just direct complements, is quite strong. For example, since every coset V plus S has this form, little t plus S, now remember, T now is a subspace. It's a complement of S. If a set of vectors X spans the subspace T, then any member of capital T, little t, is a linear combination of vectors from X, and so V plus S is equal to T plus S. V is any vector. We have our coset here, V plus S. That has the form as equal to T plus S. That we can replace T by this linear combination. Coset arithmetic, and by that I mean the coset operations of a coset addition and scalar multiplication, allow us to write it this way. And this is a linear combination of these cosets that come from this set X mod S. So if X spans T, X mod S spans V mod S. Also, if X is linearly independent, as X is a subset of T and it's linearly independent, then X mod S is linearly independent in the vector space V mod S. Because if we take some vectors from X and we form the cosets, take a linear combination, set it equal to 0. Remember, this is the 0 vector in the quotient space. Then we can write this way. And so this linear combination belongs to capital S. But it also belongs to capital T because these vectors are in X, which is a subset of T. And so this linear combination is again in the intersection of S and T, which is trivial, which means this sum is equal to 0. This linear combination is equal to 0, but the vectors V are linearly independent, and so the coefficients are 0. These coefficients are 0. Therefore, these cosets are linearly independent in the quotient space. So both the spanning property applied to T and linear independence within T imply that the corresponding cosets either span V mod S, which is T mod S, or in the second case are linearly independent. Spanning property independence transfers from T to the quotient space. That's the content of this theorem. And part 3 then says that if B is a basis for this transversal subspace, then B mod S is a basis for V mod S. This is a primary way to get a basis for the quotient space. You have to find a direct complement of S, call it T, and then you find a basis for T. In particular, the dimension of V mod S is the dimension of T, because it's the size of a basis for T, which is the same as the size of a basis for V mod S. In particular, when V is finite dimensional, remember that the dimension of a complement of S is the dimension of V minus the dimension of S. So we have this formula. The dimension of the quotient space has a name. It's called the co-dimension of the space, subspace S. And I'll use the notation CODIM for codimension. So the codimension of S, and I subscript it with V because S depends on, is the subspace of V, is the dimension of V mod S. Now, as I mentioned earlier, the fact that coset representatives are not unique, that any vector in a coset represents the coset does have some baggage associated with it that one needs to be careful about. In particular, it does complicate the issue of defining a function on a quotient space. We're interested in linear functions mostly, but we have this issue that when you define a function on a quotient space, if you do so using coset representatives in any way, you must show that your definition does not depend on the choice of coset representative for a given coset. As an example, let's look at this two-dimensional subspace of R4 and consider the quotient space. Now, when you take R4 and you factor out a two-dimensional subspace, you might suspect that the quotient space should be two-dimensional, which it is according to our formula here, and therefore isomorphic to R2 in some reasonable way, some natural way. I mean, these are isomorphic based on their dimensions, but we're more interested in an actual isomorphism. Well, one way you might try to find an isomorphism is simply to define a map, sigma, from the quotient space to R2. Sigma of this coset is just the last two components here, CD. This would be valid for all vectors in R4. This is nonsense. It is not well defined because there is ambiguity here. For example, this coset can be represented also this way, different coset representative. Therefore, sigma is now confused because using this description of the coset, sigma should give 1, 1, but using this description, sigma will give 2, 2. Obvious nonsense. And the problem is that this definition of sigma uses coset representatives, which in itself is not the problem. The problem is that the definition depends on which coset representative you pick. That is fatal. How do we resolve this? How do we find a proper isomorphism here? Well, we need to identify a specific coset representative from each coset and write the coset that way and only that way. But also, to define a linear map, the usual way is to start with a basis, and then upon which you can assign the basis vectors any way you want, and then use the fundamental theorem of linear transformations to extend by linearity. So, this set is a basis for a complement of S, call it T. And so, as we've seen, this forms a basis. These two cosets form a basis for the quotient space. Now we want to define a linear map by saying what happens to the basis vectors. here is where we need to be careful about the ambiguity that can arise if our definition depends on the choice of coset representative. So we set tau, this is our map, of this coset to be these two, the last two. But don't panic yet. We do the same thing for tau of the other basis vector. Okay, and then once we get past this ambiguity problem, we would extend by linearity. Defining tau on the basis, on this particular basis, that does not remove the ambiguity. It's just the first step in trying to define a linear map. What removes the ambiguity is that you can put any coset representative you want here, but this stays 2, 1. Okay. So if you take any vector little v in this coset, tau of that v plus s, it's the same coset as this, therefore it's the same value. So this does not depend on the choice of coset representative because we specifically use this representative to define tau, both cases here. See, before, right here, I didn't say for a specific choice of coset representative. I said for all representatives. That is ambiguous. This is not. It's a subtle difference at first, so you need to think about it until it makes sense. Okay. If this is troubling you after you think about it for a while, maybe a somewhat silly analogy might help. Suppose that we were at a university, we wanted to define the height of a classroom full of students. And we said, we'll define it to be the height of any randomly chosen student. Well, that's a problem because from 1 minute to the next, we might choose a different student. They're randomly selected. We'd get different heights. And so we don't have a well-defined notion of the height of the classroom or the height of the group of students in the classroom. We could put it that way if this is a silly example, but I mean, still it makes a point. But if we go from classroom to classroom and we select a particular student, fix that student and don't change them, now we can say the height of the class is the height of that particular student. That is a well-defined definition. That's exactly what's going on here. The cosets are the classrooms. The coset representatives are the students. We've got to pick a single coset representative for each coset. Then we can define a function using that coset representative. We're using a transversal. But we use a subspace transversal, so we can use a basis for that subspace, and therefore we have the fundamental theorem of linear transformations at our disposal. Okay, so let's look at some examples. Let's consider this quotient space. F5 square bracket x is the polynomials of degree 5 or less over f. And we want to factor out the subspace generated by x to the fifth, all scalar multiples of x to the fifth. Initially it looks like this, all the cosets of this subspace but f5 square bracket x can be written as a direct sum of the polynomials of degree 4 or less and this subspace. So f4 square bracket x is a direct complement of this subspace. It has basis that looks like this, and so we use these as coset representatives. We get a basis for the quotient space. So in fact, the quotient space, would be, well, so therefore the quotient space now looks like this, where the representatives are linear combinations of these 5 polynomials, so the polynomials of degree 4 or less. No redundancy anymore. Different R of x, different coset. Now we can define a function. We'll extend it by linearity in a minute. We define a function sigma from the quotient space to f4 square bracket x this way. So these are specific coset representatives for each coset. K ranges from 0 to 4. This is well defined now, because we're using a specific coset representative. Or put another way, if you change the representative here, you do not change the representative here. I can put anything in here I want that stands for or represents the same coset. This does not change. So this is well defined. We can extend it by linearity. And since the extension sends a basis to a basis, this is an isomorphism. One more example. Take the quotient space f square bracket x mod f3 square bracket x. Again, it initially has this expression which is full of redundancy. Lots of p of x's will give you the same coset. But any polynomial can be written this way. We group all the terms of degree 4 or higher separately from the lower degree terms. And since q of x here belongs to f3 square bracket x degree 3 or less, we get a redundant free description of this quotient space. Q of x gets absorbed, you see. This would be this is the full expression right here, which should go here, but the q of x gets absorbed into the subspace because it has degree 3 or less. It belongs to the subspace. So all the cosets look like this. This is redundancy free. Different R of x, different coset. Now we can define a function from this quotient space to this subvector space here by sigma of x to the k, this coset represented by x to the k equal x to the k. and extend by linearity, we get an isomorphism. So if we factor out from the polynomial space the subspace of polynomials of degree 3 or less, we get a vector space, we get the vector space of polynomials that are multiples of x to the 4. If S is a subspace of V, then there is a very special map, which is often denoted by pi sub S, mapping the vector space V to the quotient space V mod S, that sends each vector to the corresponding coset. You use the vector as a coset representative. You should ask yourself the question, since quotient spaces are involved in this function, do we need to check for well-definedness? And I'll let you think about that. This map is called the natural projection, or the canonical projection of V onto V mod S. This is a surjective map, or it's just sometimes called projection mod S. But this should not be confused with the notion of projection we talked about earlier in the series, rho sub st, totally different type of projection. The natural projection is linear, and here's the reason. That's again something you should work on. Don't read this, try to do it yourself first. Natural projection is certainly surjective. As far as the kernel is concerned, a vector V is in the kernel of the natural map. I guess that's another term for it, natural map. If and only if pi s of V is 0, in other words, V plus S equals S. Okay. Here I've changed the notation deliberately so you would see this. S is the 0 vector in the quotient space. We've talked about that. So we can legitimately, and some authors do, write it simply as 0. You have to just be aware of the context. You see a 0 here. It could be the 0 in V. It's not, because of this equation. Pi s of little v belongs to the quotient V mod S. So this 0 has to be the 0 in the quotient space. In other words, it's S. And this holds if and only if V is in S. So the kernel of projection mod S is in fact S. And so the natural projection, pi sub S, defined this way, is surjective linear transformation with kernel S. Very important map, as we will see.